So today I want to talk about something that's honestly impressed me more than anything I've seen in the past couple of years in computer vision. And it's something that's not talked about very much, but that is video motion magnification. So here's an example. And what video magnification does, it's kind of like a microscope for motions. There's slight variations that are less than a pixel of this crane that's standing here, and you can't see it in the regular video. But what the motion magnification does is it takes all these frames and it's able to amplify these subtle motions. So you can think of it like a microscope for motion. So this has applications for things like vital signs, really big for structural analysis and structural engineering. And in fact, it's already in use across multiple industries. You could even do something called remote sound recovery. So there's a video that details that. I'll link that in the bio. But I want to just go over the PyTorch implementation of how to implement this. So generally, this is a pretty computationally expensive task, but in PyTorch, we can parallelize this on a GPU. A NumPy implementation is over 5 minutes, but this PyTorch implementation for this video right here, we could actually process this in less than 30 seconds. So what I have here is I'm in this notebook that we're going to be using right here because we can visualize everything that's going on and kind of understand what's happening. I also have a blog post that goes over this algorithm, and I have another blog post that goes over the theory in the background for what's going on. I'll also link those in the bio. So the code that you would actually use to process this is right here. I will give you the link to this on GitHub. I'm probably not going to walk through this because I basically have the same thing in the notebook, so you can go take a look at that. So with that being said, let's get started. So this relies on the steerable pyramid stuff that I've been posting about. I have several videos and blog posts on steerable pyramids. So what a steerable pyramid does is it decomposes images into frequencies and orientations. And you can also take a look at those posts, and I'll link those in the bio. So that being said, let's go ahead and get started. So we're going to do our library import. We're going to do this video called the crane crop, which is this video on the left, and I'll show you how to make this output. So the first thing we're going to do, we could optionally use a scale factor to improve our processing. I'm going to hit that here. So the first thing we're going to want to do, we're going to create a video capture object with our video, have some lists to store the frames. We're going to get our video sampling rate. This is going to be important for the processing. And then right here, we're just going to get the frames. So what we're doing right here is we're getting the frames with OpenCV. We're resizing, storing the original ones. This is just convenient. The frames are small and we have enough memory to do this, or else we would just convert them back. And this is the step I want to highlight right here. So what we're doing right here is I am converting this to an RGB float 32 since it comes as a uint8 BGR by default, and then I'm going to the YIC color space. This is Luma, Enphase, and Quadrature. So I think this is also called NTSC. It is similar to the YUV color space, but I do have a conversion function. It's actually based on ColorSys. It's a NumPy version of it, so it's a more efficient version than NumPy. So I have RGB to YIC, and you can see right here's the original code I based it off of. But it's a pretty simple conversion right here, and then we also go YIC back to RGB, which is another simple conversion. So that's just a basic color space conversion. Not going to go over that in too much detail, and then we resize it to our scaling, and then we drop all that. So right here, I'm going to show a sample. So right here is the first frame of the Luma channel, and if you're not familiar with the Luma channel, you could think of it as just the brightness. It has a little bit more information than just the grayscale alone. So we only perform the processing on the Luma channel, and then we add in the Luma channel back into the processed Luma channel back into the YIQ color space, and then convert back to RGB, and we get this nice video right here. So we actually don't get much of an increase if we process on the other channels, and I've done some experimenting. I think just processing the Luma channel alone seems to be the best way to do this. So here's the first frame, and here's the difference of the first and the second frames. And you can see there's a little bit of, some stuff going on right here. And I want to say I don't know exactly if this is motion. It might be noise. This flag is definitely moving around. You can see there's something right here, but there's also this stuff right here for the building. So I think this could be some noise from some of the objects in the foreground. So I don't know that an optical, we can't just take an optical flow and do this kind of thing. So we need to do something a little bit more robust, a little bit more specialized in order to get these results. So the next thing we're going to do, we're going to get these hyperparameters right here. So the first thing to do is we're going to get a reference frame. We're going to use the first frame by default. With some other aspects, we could call this the DC frame, and this is going to be referring to our phase. So this is a phase-based method. So what phase in an image is, it basically tells us where things are in an image. And you can think of a Fourier transform. You get magnitude and phase. So we're going to be modifying the phase in order to modify the motion, and we need some kind of reference to phase to say, hey, how far is this phase moved from baseline? And this is going to be our baseline right here. So video length, that's just to iterate through the frames. So a little factor to avoid zero division. We're going to use a batch size of 2. It just really depends on your GPU. I have a 6 gigabyte GPU, which I think I can go up to 4 on here, but yeah, we'll see what happens. So bandpass filters. So we have our sample frequency f of s, which means our Nyquist frequency is half of that. So we have sample frequency, and then our Nyquist frequency right here is going to be 12 hertz. So that is the most that we're going to be able to sample, and you can see that we're really targeting a very low motion. So the bandpass filtering is going to get the motions of interest. So we could do this in 2 ways. We could get a super wide band and get a bunch of stuff, or we could get a narrow band. In this case, we've already done some experimenting. We've tuned the hyperparameters, and we've actually been able to acquire these hyperparameters from the original paper, which I'll also link in the bio. And they've set these hyperparameters, and they've set that as the what basically gives good results. So I'm not going to mess with these. We're going to do attenuate other frequencies. So we're basically going to zero out all the other frequencies and use our baseline phase instead of the current frame's phase as we go through the frame. So here's our magnification factor. We're going to use a factor of 25 to get this result right here. We could go higher, we can go lower, but if we go higher, the results tend to be a little bit more blurry. So I find that in my implementation, 25 is good. I think in their implementation, they do 100, but I do some things differently when I parallelize it on the GPU. So next right here is the Gaussian kernel. So what we're going to do right here, we're just getting our kernel size from the sigma that we did. So we chose a sigma of 5, so that's going to be our standard deviation, and our k size, I think that's going to be 19. We want to get for some issues, or not issues, but just the way that the PyTorch functions that I'm using, we need to make sure that the kernel size is odd, and it actually does make a notable difference when it's even, like in the original implementation. So I make sure that it's odd right here, and I have a minimum value of 3. That's all that's doing. We're using OpenCV to get the Gaussian blur kernel based on the k size and the sigma we provide, and then we turn this 1D kernel into a 2D tensor, and then we add some extra dimensions, put it on GPU, and we run everything as a float 32. So in this notebook, you might notice that I'm converting things to float 32 or complex 64. It does make a little bit of a performance difference as opposed to using float 64 and complex 128, but we don't really get a lot of benefit from going to double precision. So we're going to go single precision for everything. So here's a image of the kernel that we're going to be using. That's just a pretty standard giant Gaussian kernel that we're going to be smoothing the phase out in. And once again, you can take a look at those articles in the bio if you're interested in how this actually works. But we're going to get a better idea as we go along. So right now we're going to get our temporal filter to temporally filter all the phases. So what we're doing right here is we're normalizing our frequencies in order to pass them into our SciPy FIR window function to get our impulse, or we could actually just pass in the f of s. So the reason why we normalize the frequencies is basically what we do when we divide it by the f of s, we basically normalize it to a range from, that's going to be 0 to 0.5. And the function actually expects us to pass it in from a range of 0 to 1, so that's why we need to multiply by 2. And that's why we do this thing right here, and it normalizes it to the Nyquist rate range of 0 to 1. So that's all we're doing right here. And so we get our bandpass, and we have this is the impulse response of the function, and we convert it to a tensor, and we add some extra. We take the FFT of it, because we're going to perform filtering in the frequency domain, and then we're going to add some extra dimensions and permute them around so we could actually do this in a one-line operation in our implementation. So here's our impulse response. So this describes the filter's response in the time domain. We're not really interested in this. You can see it's got a very nice spread because we're at a very low frequency band. So, but we're really interested in the frequency domain performance. So right here we could take SciPy signal freq z, and we can get normalized frequencies and the responses. But in this case, the complex response. But in this case, I want to normalize the frequencies to what we're actually getting. So like I said, the Nyquist frequency is 12, so we're going from 0 to 12. And I have the magnitude and phase response. And you can see right here we're roughly at about 0.2 to 0.25 in this lobe right here, and we have a pretty nice roll off. We're about 40 dB down from the peak, which is pretty good, and we kind of roll off to about 60 down as we go far off. So it's a pretty good response, is what we wanted. And we can also use a Butterworth right here, which has it's going to have a more flat response than this FIR filter. So right here, we're going to get our complex steerable pyramid. I've messed around with this with a couple options. I have a smooth suboctave option. I might make a video on this later. It's what they implement in the paper in order to use more than two suboctave filters. And we're going to use 2 suboctave filters to go half octave right here. So what suboctave filters do, it basically breaks down our decomposition into even more filters, and it gives us a better spatial coverage in the spatial domain, so we can actually amplify things even more than we would with regular full octave filters. So we're going to do that right here. And just so you know, if we use full octave filters, we're going to get 22 filters. Going to be a lot faster to do this computation, and we'll actually get a pretty good result. And we get 82 filters when we go double the orientation and go suboctave. So 22, 42 for suboctave, and then we get even more orientations and we go to 82. So this is our decomposition. So every image frame of this video, we're going to take each one and we're going to decompose it into 82 different sub-images in our pyramid decomposition. And we're going to perform the processing on each one of them, and then we're going to collapse the pyramid back into the reconstructed processed images with the motion magnification processing applied. So we're going to convert, well, first we're actually going to visualize the partition and the frequency space. So here's basically what it looks like when we stack all the filters up except for the low pass and the high pass. And the complex steerable pyramid only covers positive frequencies. Take a look at the article in the bio if you're interested in learning more. So basically gonna do a little something again. We're gonna just remap it with colors. I was able to kind of get the high frequencies and low frequencies, but I didn't bother to try to figure out how to do different orientations. But you can take a look at the bio if you want to get more info about what's going on here. So we put the filters into a PyTorch sensor, throw it on the device, do the same thing for the frames, and then we're actually going to take the DFT of the whole video at once. So we're going to load all of this into memory. So we have the video frames tensor right here. We DFT over dimensions 1 and 2. So let's say frames, tensor shape, video, DFT shape. So we have 215 frames. Here's the shape of our video, and we are going to do the DFT over these frames right here. So this is going to take the DFT of each frame using the FFT algorithm. And we're going to create a tensor to hold the create tensor to store motion DFT of motion magnified frames. And now we are ready to filter. So right here is a torch NN setup of the conv filter 2D. It is noticeably slower than the torch functional, and I'm using circular padding. So basically, we'll jump ahead to this real quick. So right before we apply the motion modification, we're going to do amplitude weighted blurring. It's optional. Basically, we just do a little weighted blur over the phase deltas that we're modifying. And if you're not sure what that is, I'll try to explain it, but it's probably best if you read the article. So we're going to just allocate a tensor to store the phase deltas as we iterate. We're going to keep repopulating it. So here's what we're going to do. We're going to iterate over the filters at every batch size. So once we do this, and levels are index parameters, so we're going to get our index 1 and index 2 in order to index chunks of our filters. So the outer loop is our filters. We're going to get our filter batch, and the next thing we're going to do is we're going to get our reference pyramid. So this build level batch function uses our complex steerable pyramid. If I can find it. Pyramid utils. Yeah, pyramid utils. Okay, so all it does is it takes the DFT of the image and the filter, multiplies them in frequency space, or performs frequency space filtering with our complex steerable pyramid filter, and we do an IFFT shift to get it back to what the FFT's functions expect, and then we perform the inverse discrete Fourier transform using the IFFT function, and that's going to get us our spatial domain pyramid decomposition for a batch of filters. So, and we also have a batch of images here. So in this case, this batch size is just going to be our reference image, so it's going to be a batch size of 1. That's why I unsqueezed the 0 to make sure the dimensions work out. And then we're going to get the reference phase with the torch angle function. So I'm going to go ahead and run this and let it just crank out. I can just pop out in another cell and just kind of display what the dimensions of certain things are. So what we do next is we iterate through all the video frames, and we're going to build the batch for the current pyramid. I'm going to reformat that. But so what we're doing right here, we do the same thing except for the current video index and the filter batch, and we get the current pyramid batch. The next thing we do is we take the phase angle of this complex value and subtract our reference phase from it to get the unwrapped phase delta. Now, unwrapped basically means, or when we say wrapped, we're talking about wrapped to usually 0 to pi, 0 to 2 pi, negative pi to pi, negative 2 pi to 2 pi. So you can see that's negative pi, and I'm guessing that's negative, I think it's negative or positive 2 pi. So it goes from negative pi to 2 pi, but what we really want is the wrapped. We assume that this is the modified delta. But basically what we do is we have some modulation or modulus operations that make it 0 to 2 pi. So I've already done this, done some processing on it, and I've done the filtering, so it's going to be, let's try this here. Yeah, so you can see that when we do this operation right here, we add pi to this delta, modulo by 2 pi, and then subtract pi from it, and we basically wrap it from negative 2 pi to pi. So if we go Put that on CPU. Put it on numpy. And we will flatten it. So you can see right here, there's kind of like a swing here. And in reality, when you go up too high, when you go up to here, it's really gonna, when you wrap it, it's gonna fold back over down to negative pi and whatnot. So we're gonna, let's just plot the temp on top of it. So you can see right here that it's wrapped. It doesn't go as far down. So that's what we're doing. We're wrapping it. We're basically making it not swing as far, not kind of flip-flop from as far as it normally does. And that's basically because when we modeled this thing out and drew this thing out in theory, we expected it to be between negative pi and positive pi. So that's basically in a nutshell why we're doing it like that. So the phase deltas. So this is where we perform the frequency domain filtering. So this right here, we take our transfer function, multiply by the FFT of the phase deltas, and we are going to do it in the first dimension. So I don't really remember what these things are shaped. Just kind of the nice part about notebooks, we're doing it over all the frames right here, 215 frames, and we have a batch size of 4. So we're doing that, then we're immediately taking the IFFT and we're taking the real portion to get the filtered phase deltas. And then the next step, we go into the second inner loop, which is we iterate back over the number of frames. So we're going to build the current pyramid batch. You notice we did this here too. We can actually place this in a data structure. I was running out of memory from this. I didn't really troubleshoot it that much. I just said, okay, I'll bite the bullet and take the extra computational hit by recomputing that. So this isn't exactly a super optimized version, but you can definitely improve this on your own if you want to. So we're going to take the phase deltas, we're going to perform amplitude weighted blurring, and like we talked about earlier, this is just a weighted Gaussian filtering. We could do it in this 2-liner right here using torch NN, but it is noticeably slower. And then we get the weighted phase deltas, so we just divide by the weight. That's part of the amplitude weighted filtering. And here's the important step right here. The step you've all been waiting for is the phase modification, where we actually modify the motion. So all we're doing here is we're taking the phase delta, basically the amount of phase change between frames, and we're increasing it or decreasing it, or magnifying the motion, or we're decreasing it, we're taking the motion away or stabilizing things. So we modify this phase delta. Remember, phase tells us where things are in an image. And when we have phase changes, that means objects are moving. That is what's driving the phase changes. And we could see this even though the objects are moving less than a pixel. When we go to this phase-based representation from a complex steerable pyramid, it reveals these changes to us, and we can modify them in this manner. So when we're getting these tiny deltas and we modify them, these tiny deltas are coming from objects moving, and we modify them, we're exaggerating how much they're moving. And in turn, when we, at the end of this processing, sorry about that. So at the end of this processing, we're getting this video right here of the crane swaying in the wind, even though it's imperceptible in the real video. So another thing right here that we're doing, and this is the attenuate. So I haven't noticed a visible difference from doing this. So what this does is this takes this current pyramid level. Without this, we just have the current pyramid level that we add the modified phase to. But when we do this, we take the absolute value or the magnitude of the current pyramid. And what that does is it basically deletes all the phase information. It keeps all the magnitude tells us how things are distributed across frequency, but this basically deletes all the phase. So what this does right here, this next part right here, it adds the reference information that's normalized. So it basically scales it by the phase information from our reference pyramid in order to get some kind of phase information to do the reconstruction, because if we don't have phase information, we cannot reconstruct the image. And I'll encourage you to watch my video on complex steerable pyramids that goes over this, does the experiment, and talks about the importance of phase in an image. So the next thing to do is we take our current pyramid and we apply the modified phase to. So we put the phase offset in a complex exponential, that's 1.0j, and it's a still a torch exponential, and we multiply it by our current pyramid to accumulate the new phase. So the next thing we do is we reconstruct the filter batch. So we take our filter batch, our modified pyramid, and we go to pyramid utils. All we're doing here is we're taking the FFT of the pyramid. So we're going to frequency space, and then we are basically FFT and FFT shift. We're going to multiply it by the filter, multiply it by 2, and we're going to reaccumulate it into the reconstruction DFT. So we're going to sum across the batch here and go. And we're just going to do this through all the filters in all of our filter batch until we exhaust them. And then we're going to get to the next step, which is adding the low and the high pass component. So I've noticed that adding the high pass component doesn't actually work, and I'm actually going to comment this out. If you're interested in how it works, you can go and see the notebook. But just notice that we're actually deleting high frequency information from this reconstruction, but you're going to see that we still get a good, reconstruction video. So we're going to go ahead. Let's walk through this code real quick. So what we're doing is we're taking the low pass and the high pass from our filter tensors, and we're doing the same thing. We're just building the level right here. We're getting the current pyramid, and we're going to take the DFT of our current pyramid, and then we're going to multiply it with our high pass. So what build level does, it's the same thing as build level batch, but it basically just takes the image DFT in the filter, it does the frequency space multiplication or frequency space filtering, takes the IFFT, so we get the spatial decomposition. Here it is, spatial decomposition, and then we take the FFT of it to get the DFT, and then we multiply it by the low pass, and then get the reconstructed DFT, and we accumulate that, and we get this thing right here in frequency space. So we have a result video, so we're going to take it off, get it in the spatial domain, and remove it from CUDA. So we have the reconstructed DFT, we IFFT shift this whole thing, then we get the IFFT, take the real part, and get the video. So take it off of CUDA, just a sample right here of the first frame. So, and now we're just gonna start to inspect the results. So we're gonna iterate through the frames. We're gonna get the RGB from our BGR. We're going to convert that to YIC right here, and we're going to resize it to our original size. We're gonna scale it back up, and now we're gonna insert the YIC frame with the result. So modify YIC frame with motion magnified luma channel. We're going to convert this back to RGB. We're going to normalize it with the convert scale abs function. We could also use normalize, and we're going to append it. And now we're going to make a stacked frame. So the stacked frame is we take the BGR frames that we saved for convenience, add this horizontal column of zeros just for some padding, convert this to BGR because we're going to make a video and we're going to make a video with OpenCV. And here's a sample of the result right here, and you can see that we are, it's a little bit blurry, which is the downside, but you can't really see the motion because it's just an image. So here is the video we've made. I've already have a video saved like this, and this is the same video that we just made, and you can see that it is indeed swinging. The only downside is that the video does get a little blurry from this technique. There are some deep learning based techniques that actually make it crystal clear and even better. We can go over those in the future. So another thing I want to do, I want to show you how to visualize this magnification. So what this is right here, we take little slots of information right here across the crane on the original and reconstructed, and we can see how it's changed. So this is the crane structure. This is this little piece of imagery at each frame, all 215 frames. We can see this thing doesn't even change. And we can see right here that this thing is changing once we magnify it. And you can see that we have a little, I actually don't know what this thing is right here. I'm not sure if that's the flag or something else, but we can see that whatever it is not being magnified by our algorithm. So we can actually do another piece right here. So what I'm doing right here is I am basically converting back to RGB and taking an array so we can easily index through it. So what this part is right here is it's just this section here, and you can see that we have this cable right here on the crane and these three components, and we can see that we are rotating them. And what's interesting is these things magnify differently. So if you actually look at the first piece that we magnified, you can see that these are magnified about the same, but when we come in here, let's cheat for success. So you can see that these are magnified differently from all of these, and these right here are magnified a little bit differently from the cable wire right here. So this kind of shows that this isn't just a fancy video effect. This isn't some mindless motion magnification. This is actually adapting to the localized regions of the image and applying the magnification according to how the object is actually moving at different locations in the image across the video. So that's about it for this, and I know it was a lot, but hopefully you learned a little bit about video magnification. There's actually quite a bit of methods to do this. That it's in use across multiple industries, especially with anything structural. It makes a low-cost structural analysis because it's not always easy to fit stuff with sensors and whatnot. So that's all for this one. I will see you in the next one.